This is the transmission modulated PCD that was invented here. And it basically involves a transmitting and receiving coil. We operate at around 500 megahertz. And the RF going from the transmitting coil through the sample to the receiving coil is modulated by the conductivity of the sample. Now the sample conductivity changes if a pulse is incident on the sample. The conductivity increases, the transmission decreases, and again we see a transient. Now this has several promising advantages. By the way, it operates at 500 megahertz. It has comparable sensitivity to the RCPCD from what we can see so far, but it has a much faster response time, so we can see shorter lifetimes. And we've applied for a patent to this. We have used this technique to look at some of the nanocrystalline silicon and any number of samples, which we'll show in a bit. One of the breakthroughs that we got with this was one of the early samples, which is not shown here, which was 50-50 nanocrystalline amorphous. We got a good photoconductivity response with the Tmpcd apparatus. We had two samples that were made essentially identically, and what we see in Tmpcd is this photoconductive decay behavior. Well, what does this mean? Well, this is the response of our laser. Our laser has a full width half max of about 5 nanoseconds, so the photoconductivity is just following the rise of the laser. So the laser pulse, if we superimpose it, would be about 5 nanoseconds wide here. What we see on the other end is a characteristic that is comes from the sample itself, the photoconductive decay in the sample. We see a 12 nanosecond decay time. So the asymmetry is caused by the finite decay of minority carriers in the sample. So students have attempted to do a deconvolution of this, but kind of rough estimate is the lifetime is probably 9 or 10 nanoseconds, the difference in the symmetry of these two decay curves. Well, we decided to take a look at the photoconductive behavior of these materials. And our first shot with the Tmpcd, and we only have one, this was done at CSM, we only had a 532 nanometer YAG laser for excitation. But we did get quite a nice photoconductive signal out of this. And again, it has we can see 3 distinct lifetimes here. So there are a number of things going on here. This might be variation of the lifetime as you go along the wire. The next test would be to have a tunable system and look at these wires as we vary the excitation wavelength along the range of band gaps that the material contains. But this was a zinc, cadmium, sulfur selenide alloy. And it was quite photoconductive. This is the bottom line. So we're looking at this as a wide band gap detector or perhaps a solar converter. This would be these materials are quite easy to make compared to the tandem structures that are used in the high efficiency space photovoltaic technology. Those are quite complex and difficult and expensive to grow, whereas the nanowires will grow without strain because they're wires. They'll grow out of a substrate, and you can obtain this composition variation the length of the wire. So this has some possibilities for future generation photovoltaics.